In this video, we're going to summarize your findings from the video analysis and summarize the key ideas and show you how to work with these ideas in solving problems. So first, let's just review what you found in your video analysis. And taking a look at the graphs, this was our graph for the horizontal position of the ball when it was flying through the air and it was off the table. And I had a slope of 1.5 meters per second. So, and my mathematical model was that the horizontal position of the ball equals 1.5 meters per second times the time, telling me that while it was in the air, it was moving sideways at the same rate that it had been moving when it was on the table, because this is the same velocity that I had when I did video analysis for the ball on the table. So when it was on the table, it was moving at a certain rate. When it went off the table, it continued to move sideways at the same rate, even though it was falling downward at the same time. So horizontally, we have a constant velocity motion for an object that is in projectile motion. Now what about vertically? What's happening? Vertically, I have a quadratic as my best fit, and my equation was y equals a t squared, where a was negative 4.9 meters per second squared. Now, when you match this up with the kinematics equations, the closest one is delta y equals v initial delta t plus 1/2 a delta t squared. And this is just to review. Hopefully you were able to match these up, but if not, this will help clarify that. So you can see that the t squared and the delta t squared, those match up. And the thing multiplied by the time squared is this. So these things match up. This must be 0 in our scenario, which makes sense because vi is the initial vertical velocity and it wasn't moving vertically when it first went off the table. And then y matches up here. So this tells us that 1/2 a must be equal to negative 4.9. Well, how could I rewrite this constant so that it's in the form of 1/2 times some number? Well, I'm going to need to know what double this is. So if you multiply 4.9 times 2, you get 9.8. So I'm going to rewrite this now as 1/2 times negative 9.8. meters per second squared. Okay, so that is the same thing as this. So negative 4.9 meters per second squared is the same thing as 1/2 times negative 9.8 meters per second squared. And you can see now it's in the same format as our kinematics equation, which gives us a clue that this number right here is the acceleration. And you'll recognize that is the acceleration of an object in free fall with no air resistance. So this tells us that a projectile, even though it's moving sideways, is falling at exactly the same rate as an object that is dropped or an object that is thrown upward into the air after its release. So now we're ready for our summary. You have the standard details up at the top, but let's go over the key ideas. The horizontal aspect of a projectile's motion can be modeled as constant velocity. And the vertical aspect of a projectile's motion can be modeled as constant acceleration. So the really nice thing about projectile motion is it's using models that you already know. And it's just that we're going to use both of these models now at the same time. How does the horizontal movement of a projectile affect its vertical movement? It doesn't. They are what we would call independent. Okay, the horizontal movement has nothing to do with the rate of progress of the vertical movement. Okay, here we have a specific example. We're going to analyze the force, but before we do that, I want to just explain the picture here. This is a cliff. I've put my origin here at the corner of the cliff. We have a ball that's rolling along, and it's going to roll off the table with an initial horizontal velocity. And I have plotted its position at 3 different times. And in the table here, you can see the times. So time 0, time 1/2 a second, time 1 second, and time 1.5 seconds. And then the x column is the horizontal position, and y is the vertical position. So remember, this is the origin here. So this means at time 0, it was at the origin. Then at time 1/2 second, the horizontal position was 7. And my scale is that a 1/4 inch, which is 1 square, is 1 meter. So 7 meters would be 7 squares. So 1, 2, 3, 4, 5, 6, 7. And then the y position is negative 1.2. So remember, this is the y equals 0. So I have to go down 1.2 squares, and that's the position. Similarly, at 1 second, the x is 14. So twice as much time, so it's gone twice as far sideways. That's constant velocity. But vertically now it's at negative 4.9. So you have to go down 1, 2, 3, 4, 4.9, and that's where it is. Okay? And then this is the last position. So on your picture, draw in as best you can a smooth rendition of the path, followed by the projectile. Now what we want to do is analyze the force. Draw the forces on the projectile at each position. So at time 1/2 a second, what forces would be acting? Well, there's no air resistance, and it's not interacting with anything then except for the Earth, so we have a force of gravity. So I'm going to draw a downward arrow and label it as Fg. Now at a later time, there are no new interactions, and the mass of the object hasn't changed, so it has the same force of gravity. So draw another arrow with the same, try to make it the same length as your first one. And the same thing on the last diagram, the last position. Okay, and these free body diagrams really help to illustrate why we have constant velocity horizontally and constant acceleration vertically. We have constant acceleration vertically because there's an unbalanced force in the vertical direction. We have constant velocity horizontally because horizontally we have balanced forces, meaning they're basically, in this situation, no forces horizontally. So horizontally, it has constant velocity. Vertically, it has constant acceleration. Now the next step is to talk about, where did I get these numbers? How did I know that this is where the object was at these different times? So to explain that, I'm going to need to show you first how to list variables. So turn to the back side and go down halfway down the page where it says how to list variables. Whenever you're working with projectile motion, you have to always make 2 separate lists of variables. One for the horizontal motion and one for the vertical. And I usually just label them horizontal and vertical. Now horizontally, we have constant velocity. So the variables there will be delta x, Vx, or you can call it Vc for constant if you want, and the time. Those are the variables for something moving at a constant velocity. Vertically, we have constant acceleration. So that means we're going to need a different list. We need the initial velocity, but I'm going to put a little y to help us remember that this is the initial vertical velocity, and Vf, but I'm going to put a little y to remind us that this is the final vertical velocity, final meaning at whatever time you're talking about. We have our vertical acceleration, and we have the time. Now, because we're dealing with projectiles that are flying through the air, if you're at the surface of the Earth, you know the acceleration vertically is negative 9.8 meters per second squared. If you have a projectile on the moon, you would need to use the appropriate number for the moon. The other thing to realize about these 2 lists is that for any moment in time that you're looking for information, the times here are the same. So if you're talking about 0.5 seconds, this would be 0.5 seconds and this would be 0.5 seconds. And then this would give you the vertical displacement at that time. This would give you the horizontal displacement at that time. So let's do one example to show where one of those, how I knew the x and the y on the other side of the page. So we initially know, I think we know this velocity, right? We have given to us that the horizontal velocity is 14 meters per second. And that's going to stay constant for every time that you look at in the motion. Vertically, we want to find the y position and the x position. Vertically, what is the initial vertical velocity? When it first leaves the table, when it first begins to be a projectile, is right here. And right here, it has no vertical velocity. If it had been launched this way, then it would have some horizontal and some vertical. But if it's launched horizontally, the initial vertical velocity is 0. So this is 0. And now we're ready to find delta y. So delta y equals v initial y delta t plus 1/2 a delta t squared. This is the equation that does not have vfy, so it would let us find delta y. The initial vertical velocity is 0, so I have 1/2 times negative 9.8 meters per second squared times 0.5 seconds squared. And calculating that, we have 0.5 times negative 9.8 times 0.5 squared, which is negative 1.2 meters, which if you check the other side of the paper, that was what I had in the chart for the y position. Now the reason this is delta y and not y, it just means the change in position. Since it started at 0, delta y is the same as y. We can also find the horizontal position, remembering a relationship for constant velocity. Vx is delta x over delta t, or maybe you prefer to write it delta x equals Vx times delta t. And then substituting, we have 14 meters per second times delta t, which is 0.5 seconds, and that gives us a position of 7 meters. So whenever you're solving problems with projectile motion, be sure you make 2 lists of variables, one for the horizontal aspect of the motion and one for the vertical aspect of the motion. Okay, our next task is to talk about the velocity at different times in the motion. This is the same picture that you had on the other side, so same horizontal velocity, same scale, same chart of positions. What I've done now, though, is I have drawn the velocity of the projectile, but I've drawn the components. So let's read what it says here. The direction of a projectile's velocity is tangent to its path at any moment. The horizontal component of this velocity, which we call Vx, is constant. The vertical component, Vfy, is changing. To find the projectile's velocity at a moment in time, you have to add these vector components. In this chart, I've listed the components. You can see that the horizontal component of the object's overall velocity is constant. It's moving sideways at the same rate no matter what time you're talking about. Vertically, though, its change in position over time is increasing. It's going faster downward as more time goes on because it's accelerating in the downward direction. Now, what I did on the diagram was I drew these velocity vectors to scale. So first let's look at the horizontal ones. So at time 0, 14 meters per second. I used a scale of 1 centimeter is 10 meters per second. So I drew here Vx as a velocity vector that's 1.4 centimeters long. Then at half a second, it's still moving sideways at that same rate. So here's the horizontal component of its velocity at that time, the horizontal part. At 1 second, it's still moving sideways at the same rate. So once again, Vx is the same, it's still 14. And at 1.5 seconds, Vx is still 14. Now the vertical velocities are changing. So at time 0, there's no vertical velocity, so you don't see an up or a down arrow. At half a second, the vertical velocity is negative 4.9. That's represented by this arrow. At 1 second, the vertical part of the velocity is negative 9.8 meters per second. So notice this is a longer arrow than here. And at 1.5 seconds, the vertical velocity is even larger. Now you might say, well, but what's the object's velocity? Well, the object's velocity is the combination of these two. So to draw it, you have to add these as vectors. So let's do that. Let's do this one, and then you have to add this to the end of it. So I'm going to draw this vector at the end here so that we can add them. and you'll get an arrow that looks like this, that's tangent to the path. Now let's add these two together. Vx plus Vfy, you could do this with a ruler to make it more precise, equals the velocity. So this is the velocity at that time. This is the velocity at that time. And then we can add these. And this is the velocity at this time. You can see that these resultant vectors are getting longer. That's telling you that the speed, the magnitude of this is the speed of the object is increasing. Now, how did I find these values for the components? Well, the horizontal component I know because it was given and it doesn't change. The vertical component you can calculate when you're making other calculations. So you just solve for this. So you would probably use this equation, Vfy equals V initial y plus A delta t. And the purpose of putting the little subscript y's is to remind yourself this is vertical. It's the initial vertical velocity. This is the vertical velocity at some later time. Okay, now how would you calculate this resultant vector? Well, you could draw a diagram to scale with your protractor and your ruler, or you could use the little velocity triangle. So let's find the velocity, magnitude, and direction at 1/2 second. So Vx is 14. Vfy is what at that time? Negative 4.9. The negative just means it's downwards, so this arrow is 4.9 in length. And then what I want is this. This is the actual velocity right here. These are just the components of the velocity. So I can use the Pythagorean theorem with my triangle to find that hypotenuse. So 14 squared plus 4.9 squared, and then the square root of the result. So the result for the velocity is 14.8 meters per second. Oops, not the velocity squared, that's the velocity. So that is the actual magnitude of the object's velocity at 1/2 second. That is the speed of the object at that moment. This is its horizontal progress and vertical progress, but overall, if it had like a speedometer attached to it, this is what the speedometer would say. But this is not the whole velocity, that's just the magnitude of it. We need to find the angle if we're stating a velocity. Velocity always has a magnitude and a direction. So we can do that using tangent. Theta is opposite over adjacent. And using our triangle, opposite is 4.9 meters per second over 14 meters per second. And then using inverse tangent of this fraction, 4.9 divided by 14, inverse tangent is 19 degrees. But you always have to be careful where that is measured from. That is below the horizontal. So you could say that the velocity is 19 degrees below the horizontal, or you could give the angle, from the positive x-axis, which is what we usually do. Then it would be 360 minus 19, which is 341. So to state the final velocity, we would say that the velocity is 14.8 meters per second at 341 degrees. Okay, that is the velocity at this time. If you wanted to find the velocity at another time, you already know Vx. You would have to find Vfy using the equation down here. And then add them together as vectors. Okay, projectiles launched at an angle, you will learn that in a video in the homework. Right now what I'd like to do is just work one more example with you of how to solve problems involving horizontally launched projectiles, and then that will be it for the lesson. So practice. A baseball is thrown horizontally with a velocity of 40.2 meters per second from a height of 1.3 meters. Where will it land and how long was it in the air? So always get clear on your situation. So I guess we don't have a cliff really so much here as we have a person throwing a ball. And it has initially a horizontal speed of 40.2 meters per second. And it's going to go like this. The initial height is 1.3 meters. We want to know where will it land. So we know it's going to land down 1.3 meters, but what they really want to know here is what is this? What's the horizontal distance? And what was the time it was in the air? Remember always to make your two lists of variables. Horizontally, constant velocity, so just 3 variables in that list. Vertically, we have constant acceleration, so you need your acceleration variables. Okay, then figure out what you have. Remember, be really careful about negative signs. So 40.2, what is that? That looks like the initial velocity, and because it's all horizontal, it would be Vx. So 40.2 meters per second. Let's see. I don't know delta x. I don't know the time it was in the air. Do I know delta y? Well, the point in time I'm interested in is here, when it lands, and the delta y, the displacement from there to there, is negative 1.3. It was downward 1.3 meters from where it started. Initial vertical velocity. Whenever you see this, translate it to initial vertical velocity. Initially, it did not have any vertical velocity, so this is 0. Finally, the velocity, at this time, the velocity would be tangent to the path. Finally, it would have a horizontal velocity component and a VFY, so I don't know what that is. And acceleration, negative 9.8 meters per second squared. And I don't know the time, but these times are the same. So let's see, where will it land and how long was it in the air? Where will it land? That's delta x. Well, I have 2 unknowns over here, so there's no way I can find anything yet. I think I'm going to need to know the time before I can find that. So let's look at the vertical list. What could I find? How long was it in the air? Maybe I could find the time. I have 3 things, so I should be able to find the 4th one. So let's see, look at your list of equations. The one you're going to want is this one. And substitute your values. VIY is 0, so this term goes away. 1/2 times negative 9.8. And you can solve for delta t. To do that, you need to multiply, let's see, we could divide this first, I guess. So negative 4.9 times delta t squared, then divide both sides by negative 4.9. (1.3) divided by 4.9 is 0.2653 and a bunch of other things. And then taking the square root is 0.52 seconds. Okay, so it landed at 0.52 seconds. That's how long it was in the air. Then where will it land? That's going to be delta x. So delta x equals Vx times delta t. And Vx is 40.2 meters per second. Delta t is 0.52 seconds. So multiplying that, we got 21 meters. Okay, so where will it land? It will land 21 meters away from where it was released, and it will be in the air for 0.52 seconds.